Hi, this is Gabriel Chen. Welcome to Lab 3. The purpose of this lab was to examine the orbit of a star around a black hole of unknown mass through the lens of a perpendicular and parallel force components. This is modeled solely on a computational model through FlowScript, where the black hole's mass position was generated through a seed. By examining the change in momentum with respect to time, in perpendicular and parallel directions, and through the equation for gravitational force, we can predict the mass of the black hole given the star's mass and trajectory. In our model, we simplified the time step to be 1 day, and we started with a stellar mass of 2 times 10 to the 30 kilograms, and we generated our seed through our user email. This was the code for our model. As you can see in line 11, we set our seed to our tech email, and the rest of the code on this page is the generation of the black hole and the star trajectory. Lines 119 through line 128 are used to set our initial conditions, while lines 155 to the end of the code are used to keep track of our force components, our momentum components, velocity components, and also to calculate our mass at each time step. The last 5 lines simply print out our net force's magnitude alongside its components' magnitudes, alongside the mass of the black hole itself. This is a recording of our simulation. The observed forces were as expected. As the star goes closer to the black hole, the net force increases drastically, and the net force is drastically smaller on the far side of the elliptical orbit. This is the expected result since the force of gravity operates on the inverse square principle, meaning reducing the distance by 1/2 increases the force's magnitude by a multiple of 4. Furthermore, the perpendicular component becomes a significantly larger component of the net force compared to the parallel component near the black hole as well. This is necessary for the star to not be dragged into the black hole as a perpendicular component is sufficient magnitude as it drives the star forward away from the black hole and stops it from spiraling to its death in the belly of the black hole. It is worth noting that the perpendicular and parallel components of the force are mathematically equivalent to the perpendicular and parallel components of the rate of change of momentum have their own nuances. Primarily, the force components cannot be directly measured. However, we can track the star's velocity, and through this we can track the star's momentum and thus its rate of change in momentum. There isn't some tool that we can use on the star that tells us the magnitude of the forces acting on it. That force must be calculated. Another interesting thing is that even if we had some way to magically detect the forces acting on the star due to the black hole, if that black hole was instantaneously replaced by another black hole, we would not need to recalculate the black hole's mass if the star trajectory remained unchanged. This is because the star trajectory is dependent on the black hole's mass as seen by the equation for gravitational force. The only considerations are the masses of two objects and their distance. If the star's mass and distance is unaltered after the swap, it can only mean that the new black hole was of equal mass. We can never tell that a swap had even occurred solely by observing the star's trajectory. The code kept track of the star's momentum, and we had our time step, so we were able to find the rate of change of momentum and thus the net force, which we then set equal to the gravitational force equation. And since we already had the star's mass and the distance, we were able to calculate the black hole's mass. We found the black hole's mass to be 9.2 times 10 to the 33 kilograms. There were some fluctuations in our calculations, but we believe that was due to simplifications in our model parameters, such as our large time step of 1 day. Through these principles, we were able to examine how the net force's components affected the star trajectory, as well as calculate the mass of a black hole given the star's trajectory.